So it is difficult to keep one variable, pressure, volume, or temperature constant at all times. And this new law combines Boyle's and Charles's laws. You have, here's Boyle's law with pressure and volume, and here is Charles's law with volume and temperature. All right. So if you don't use one of these variables, you just cross it out. All right, you don't have to, and that leaves you with one or the other. So that does make it easier. Also, you only have to remember one thing. Remember, very important is the temperature has to be in Kelvin. All right, so we have a bike tire inflated to a pressure of 2 atmospheres. So I've got a pressure. My initial pressure is 2 atmospheres. And I have a temperature, right? I have initial temperature of 300 kelvins. All right. Now the temperature is going to go down so my second temperature is going to be 278. So the temperature is going down. It says, what is the new pressure? All right. So I've got pressure and temperature here. So I will just ignore the volume and I'll use my, what I'm trying to find is the new pressure. So I'm going to use this combined law. Oops. All right, and I've got PV over T equals PV over T. All right, so we're not talking about any, there's nothing about volume, so I'm going to ignore the volume. All right, and so what this is showing me is that pressure and temperature are also directly related. If one goes up, the other goes up. If one goes down, the other goes down. So since my temperature went down, I'm thinking my pressure is going to go down too. So let's see, let's substitute in what we've got. My initial pressure is 2 atmospheres and the initial temperature is 300. And I do not know what the new pressure is, so that's my variable, my new pressure. And then my new temperature, though, is 278. It went down, right? It started out at 300 and it went to 278, 300 to 278. So my pressure is also going to go down. Now to see what it is, I'm going to cross multiply, so I get 300 times P2 equals 2 times 278. All right, now I want this pressure all by itself, so I'm going to divide by 300, that's 1, and so I have to do that on the other side, right? So now I'm going to do that in Desmos. I'm going to put 2 times 278, all right, and all of that divided by 300. And so I get 1.85 as my new pressure. All right, so my new pressure is 1.85. And then look at my units. In your answer here in my equation, I don't put the units, but it's very important at the end to write the units. And so I've got atmospheres, and this is my final answer. Okay, the question was, what is the new pressure? And I found a pressure, all right? And it went down, right? Temperature went down, so pressure went down. All right, very good. So you can solve all kinds of problems with this one combined gas law. All right, so let's do another one. It says a sample of gas. These are actually some of my favorite there's so many favorite chemistry problems. These are one of it. Dimensional analysis I love, And this I love, gas problems. All right, so here we go. We have a sample gas. It has a temperature of 150 Celsius. Remember, it has to be in Kelvin. So first thing I'm going to do, I'm going to take that 150 degrees Celsius. And what's the magic number for Kelvin? 273. So I'm going to add that up, and I get 300. 2 and 1 is 3. Oh, no, that's going to be 4. Let me erase that. I don't know if this, I can do this. There we go. Okay. All right, so maybe I'll start with the ones. So 3 plus 0, 7 and 5 is 12. And then, so I've got 423. All right. And I had Desmos over here. I could just add that up there real quickly, right? 150 plus 273. I don't need to impress anyone. 423. All right, so there we go. So that's you have to have Kelvin. That's very important. So now I'm looking at my givens. So that was given to me, right? I had to do a little bit of work, but basically I had my initial temperature is 423 kelvins. All right. I have a volume of, so my initial volume is 10.2 liters. And the volume is changed to, so my new volume is going to be 16. So the volume goes up, all right? And the question is, what is the new temperature? All right, so if you heat up a gas, right, oh, actually, I don't know what I'm doing to my gas, but I do know that I'm getting, my molecules actually are, oops, I don't want to draw that. My molecules are spreading out, right? Because my volume is bigger. I have a bigger volume. So the volume went up. It went from 10 to 16. So volume went up. So that means my, that would be, I've got a higher kinetic energy, all right, of my molecules. Let's see how that turns out actually. Because that could be, the temperature could go down. If you let your molecules spread out, they cool off, all right? That's why it gets cold at a high altitude, all right? But then that's low pressure. So here everything's all complicated. You know, it's hard to isolate your variables. Like, so that's why we have this equation. We'll just use this. PV over T equals PV over T. All right. Now I don't know anything about the pressure, so I'm going to assume the pressure is constant, and I'll just look at my volume and temperature, and so I can see that they're directly related. Okay. If the pressure is constant, they're directly related. So if the volume goes up, the temperature is going to go up. All right, so that's the equation. Let's substitute in. So I have my volume. My first volume was 10.2, and the temperature with that was 423. And then my new volume was 16.2, and I don't know the new temperature. All right, so now I'm going to cross multiply. And I'm going to get 10.2 times that new temperature equals 423 times 16.2. All right, now I want to solve for that temperature, so I'm going to divide by 10.2. And I like to do that all at the end, okay? So anything divided by itself is 1. So I know that my new temperature is going to be, and let's go up here. Well, I guess we'll start over. I've got 423 times 10.2. Oh no, 16.2. It's hard to read my writing. Save yourself some grief and write carefully, write neatly. Divided by 10.2. All right, so looky there. It did go up. My temperature went up to 671.8 kelvins. All right, if I want just 3 significant digits, I will make that 672 kelvins. Okay. All right, very good. So, what if we want to incorporate the amount of gas that is present in the sample? Can we do this with the equations we have learned thus far? All right, that's the question. What do you think? Well, no, we didn't talk about the number of moles that were there or the number of particles. So this brings us to the ideal gas law. PV equals nRT. And it's really easy because basically we already know most of this. We know pressure times volume, right? There's Boyle's law. And then we just bring the T on the other side, right? So volume and temperature are directly related, right? And that is a direct relationship if they're on opposite sides. So that's Boyle's law and Charles' law there. Now we're just adding these constants here. So N is actually the number of moles. All right. How the big gases act, and it makes sense. You saw this in the PhET lab, that the number of particles you have definitely affects how the gases behave. And so this incorporates that. Now this is a constant, and remember pressure can have different units. So you have different, depending on the units, you have different constants. All right, so you just have to pay attention to the units. And then the constant this will be given to you. You're not going to have to memorize those. All right, so here we go. All right, so this is basically right here. It's just saying that all these things are, they vary. They vary directly and inversely. And they kind of, one affects the other. All right, so we can put them all together in this equation. And N is the number of moles of gas. R is your ideal gas constant. And like I said, it can be either of these 3 numbers depending on if your pressure is in kilopascals, atmospheres, or millimeters of mercury. All right, notice you always use Kelvin for the temperature. And notice here, you always use liters. All right, and the other problems I wasn't worrying about if I had liters. But if I'm going to be using this constant here, I have to have these units. All right, so now we've got to make sure we have liters as well as kelvins. All right. And like I said, you don't have to memorize the R values. And the beauty is the steps are the same. That's why we learn algebra. All right, algebra is the tool to solve anything for any class. And here we go. So you have a sample of hydrogen gas. This is important. These are gas laws. I have cubic decimeters. All right. So now I need to know, well, how many liters is that? Okay, so I'm going back to earlier in the slides. Volume. All right, we need to remember these conversion factors. So 1 cubic centimeter is 1 milliliter. All right. And 1,000 milliliters is 1 liter, okay? And 1 cubic decimeter is 1 liter, okay? So this has to do with this problem that we're doing right now. A cubic deciliter is a liter, all right? So that's nice. I can just convert that to an L, and I'm good to go. Okay, so I've got for my volume, my first volume is 5.7. Instead of decimeters, I'm going to go ahead and put liters. All right. And I've got a pressure of 200 kilopascals. All right. And I've got a temperature of 288. Kelvins, and the sample contains how many moles? So I'm trying to find N. That's what I don't know. So I need to figure out what constant I'm going to use. Let me go back. I've got liters, kilopascals, and kelvins. So let me see what that would be. Liters, kilopascals, and kelvins. So I'm going to use the 8.314. So that's pi. That's kind of like pi, 8 pi. That's how I'm going to remember that. 8.314. Okay. So now I'm just going to put that, my unknown is the number of moles here. My equation is this PV, Boyle's law, equals N R. And remember, volume and temperature are directly related. That's Charles' law. So, and here's my constants right here. All right. So, there's my equation. Oops. And now I'm going to substitute into there. All right. So my pressure is 200. And remember, don't use the units when you're doing your algebra. That's just for your when you're writing out what you're given and your final answer. My initial volume is 5.7. I do not know the number of moles. I'm going to use 8.314 for my constant, and my temperature is 288. Okay, so now I want to know N, right? And these are all multiplied together. So how do I get rid of them? I divide by that. That gets rid of that. And I'm going to divide by that. And that gets rid of that. If I do that on that side, I need to do that on this side. So I'm going to divide by 8.314 and 288. So this gives me N all by itself. The number of moles is this. And so I'm going to put this into Desmos. I'm going to go ahead and make that a fraction right away. It just makes it a little bit easier. And I've got 200 times 5.7. And I'm dividing by my constant, 8.314 times the temperature, 288. Okay, and then now I can see that gives me the number of moles is, let's see, how many do I have? I've got three significant digits. So here we go. 4, 7, 6 moles. Alrighty. And that's it. So this is not hard. Maybe that's why I like it. I thought it was because I like math. Maybe I like it because it's easy. You just have to be, you have a system here. Writing things out, you have to be systematic. Don't try to do it all in your head. Okay, so a gas cylinder, gas laws, boom. 4 moles. That tells me, boom, my equation. If I'm talking about gas laws and moles, I'm using this. And just to confirm, you always look at what you're given. Let's see, I've got a temperature. And thank goodness it's already in kelvins. How nice. A piston is compressed to yield a pressure of 400, P equals 400.0 kilopascals. What is the volume inside the cylinder? So that's my unknown. I'm trying to find the volume. All right. So now I need to figure out my R, which R I'm going to use, which constant. So I look at the unit again. I've got kilopascals. I think that's what I had last time, right? When we used, yeah, kilopascals is the 8.314. So, kilopascals, 8.314. So you said you don't have to memorize these, but like it's just like with all this, the more you practice, you will actually start to memorize these things. Now I'm going to substitute in pressure, P, 400.0 times volume. Oh, I don't know what that is, so that's V. Number of moles. Oh, I forgot to write that down. It was given to me. Number of moles is 4 moles. All right, so that's 4. My ideal gas constant is 8.314. And temperature is 300. Okay. So here's my volume that I want. Let's get it all by itself. Let's divide by 400. 0.0. Boom. Right? Anything divided by itself is 1. Got to do it on both sides. Okay. So that gives me volume equals whatever that is. So let's do that. I've got 4 times 8.314 times 300. Oh, I forgot to make my fraction first. No worries. I'm just going to highlight that, and I'll hit divided by 400.0. So I get 24.9. And let's see, for the volume. So 24.9. I might go ahead and do the 9-4 and then have 4 significant digits. Oh, and I forgot my unit, volume. That's got to be liters, right? Got to be liters. Okay, very good. Yay, yay us. What's the next one? Example 3. A sample of gas. Okay, so I'm thinking gas laws. A cubic decimeter, that's just a liter. All right, so I've got my volume is 4.5 liters. And I've got 6.7 moles, so N equals 6.7 moles. My pressure is 1.6 atmospheres. And that's really important because that's going to be a different R, right? That's going to be a different ideal gas constant. That's not going to be that one we've been using. So let's go up and see, because we don't have to memorize it, but we do have to remember to look for it. So atmospheres is going to be 0.08, so it has an 8 as well, but now a 21. 0.0821. So here we go. So 0.0821. All right, so now what am I trying to find? That says what's the temperature? All right, so my unknown is the temperature. That's what I'm trying to find. What is the temperature? So I've got my trusty PV equals nRT. And then I'm going to substitute. P is 1.6. Volume is 4.5. Number of moles, 6.7. R is 0.0821. And the temperature is what I'm trying to find. All right, so that is, again, the beauty of algebra. You just write your formula, substitute in, and then now you get your variable by itself. So everything's multiplied. So I'm going to divide by 6.7. That makes that go away. Got to do it on both sides. Got to divide this guy out. So 0.0821. Boom. But got to do it on both sides. So now I have my temperature all by itself. And I'll just write this up here. Now I'm going to make my fraction, hit divided by, and then I've got 1.6 times 4.5 in my numerator, and my denominator is 6.7 divided by 0.0821. All right, and that gives me, let's see, so for my temperature, these are all to the tenths place, my volume and pressure to the tenths place, so we'll make that 13.1. So we'll say 13.1, and what's my unit for temperature? It has to be kelvins. That's okay. So there we go. That's all you gotta do. And those are the gas laws. The next thing we're talking about is partial pressures. I think we'll put that in a different video. So I'm going to stop this.